In the winter of 2009, a piece of software was released on the internet.
Digital money called Bitcoin.
Like throwing water on burning oil, it ignited.
And this is the biggest story of this decade.
Bitcoin sent shockwaves through the world, spreading like a wildfire and disrupting everything it touched. Nobody knew what it was, nobody knew how to value it, and nobody could control it. And like any new technology, it came with pushback.
The whole Bitcoin market is about $1 billion. It's a novelty for the geek squad.
On top of all of these attacks, critics came after its energy usage. That's right, Bitcoin consumes energy.
Bitcoin in general is wasteful by design.
Bitcoin uses a system called proof of work, which requires energy to function. Bitcoin uses more energy than countries like Ukraine, Norway, Sweden, Argentina, or the Philippines. Now, if you just heard of those comparisons, you're likely shocked. And here's where proof of stake comes in.
I think great things are on the other side. So number one is obviously proof of stake. So much more efficient, much more secure, much less tree killing.
Thousands of new cryptocurrencies use this new proof of stake model, all promising to be superior to the old energy-intensive proof of work technology. There's only one problem. Is this true, or are they marketing false promises?
One of my issues with sort of proof of stake, the way it's been presented and with the Ethereum roadmap, is that I think that the risks are not sort of fully discussed in a very open, intellectually honest way.
From this video, we will see the differences between proof of work and proof of stake, the problems tied to each, and whether one is more efficient than the other. Often the advantages of proof of stake are described without acknowledgement of its trade-offs compared to proof of work. To understand these trade-offs, we must first break down what proof of work is. The Bitcoin network is programmed to create a new block every 10 minutes and add that block to the blockchain. A new block is produced by a Bitcoin miner, contributing processing power to solve a cryptographic puzzle that the previous block created. At this point, the miner can package thousands of Bitcoin transactions into that block. That's how transactions get settled. The YouTube channel 3 Blue 1 Brown explains the other half of proof of work in this short clip.
Earlier, I said that the proof of work might be to find a special number so that the hash of the block starts with 60 zeros. Well, the way the actual Bitcoin protocol works is to periodically change that number of zeros so that it should take, on average, 10 minutes to find a new block. So as there are more and more miners added to the network, the challenge actually gets harder and harder in such a way that this miniature lottery only has about one winner every 10 minutes.
What 3 Blue 1 Brown just described is known as the difficulty adjustment, which occurs automatically every 2 weeks. This difficulty adjustment ensures the supply of Bitcoin remains limited. Value investor and podcast host Preston Pish explains why a difficult supply issuance is important for Bitcoin.
When I think about what worked historically before we even went into a digital space, the reason gold works so well is because it's really kind of hard to find an ounce of it in the Earth's crust because of the distribution of it and whatnot, the amount that there is. So when you look at why gold served a purpose, it's very obvious from a scarcity standpoint why. And then you look at the work that had to be performed with a shovel or whatever in order to pull it out of the ground. It makes sense real fast as to how it basically achieved its value.
Just like gold mining, Bitcoin miners put forward work or energy in order to mine new Bitcoin. And just like people value gold due to its rarity, people value Bitcoin because it's scarce and difficult to find. This process is known as proof of work. Millions of machines use electricity to apply processing power to guess the answer to a cryptographic puzzle left by the most recent block. This may seem like a waste of energy, but it's what keeps the system decentralized. No central authority determines a valid set of transactions. The more energy that Bitcoin uses, the more secure its latest transactions are against most types of attacks. Many non-Bitcoin blockchains have been victims of 51% attacks, where a single entity temporarily or permanently gains control over 51% of the processing power on the network, and uses that majority of processing power to reorganize blocks and perform double spend transactions. This shows Bitcoin's energy usage compared to the energy usage of some of the copycat networks. Those other blockchains only have 1% or less of Bitcoin's total processing power. So if just 1% of Bitcoin miners decide to do a 51% attack on either of those two hard forks, they can. However, the same is not true for the other direction, since the Bitcoin network uses far more energy. That shows the importance of network effects and why Bitcoin's energy usage has kept it secure. Bitcoin's energy usage can also benefit our global power grids, as macro investor Lynn Alden explains.
I think actually when we look out longer term, the kind of the direction that we're going, I think in proof of work, assuming these systems continue to be around for quite a while, is that you'll see increasing integration between miners and the energy producers themselves. We already see, for example, early signs of co-location, where you have an energy producer, could be solar, could be hydro, could be whatever, and they have Bitcoin miners on site. They often will contract with a miner to co-locate them, but they could easily do it in a vertically integrated model where the way that the grid works, and this is something that a lot of kind of environmental criticisms of proof of work don't understand, is that the electrical grid naturally has to overproduce electricity, right? Otherwise, if we didn't have extra productive capacity, then turning on the marginal laptop would cause a brownout, right? So we have to have this spare production always going into the network, and then we have to have a way to drain out excess power that's being produced but not consumed. And it's actually this really kind of tricky balancing act. And so proof of work systems are actually a really good load balancer, where if you're, the type of energy source that doesn't have full control over your production. Maybe you're a wind farm, maybe you're a hydro dam, maybe you're solar, or maybe you have just kind of your nuclear plant that just kind of has like continuous power, but maybe the demand is fluctuating throughout the day, right? So it's more demand at evening, less demand other times. And so I think over time, we're going to see that the cheapest source of electricity is that virtually zero cost stranded energy. And the best ones to harness that are the producers or people that contract directly with the producers and go on site. And so I think over time, that's what basically makes it as kind of diversified as possible. And right now, I think, last I checked, the biggest Bitcoin mining facility in the world is like 1% of total hash rate. It's already kind of a structurally decentralized system. And I think it only gets more so as you increasingly incorporate that into production.
Since its inception, the Bitcoin network has operated using proof of work with no plans to change. The Ethereum network also operates with proof of work, but it has future plans to switch to a proof of stake system. But what is proof of stake? Proof of stake is a system where cryptocurrency holders stake their coins, use them to vote on the valid blockchain, and get rewarded with more coins for successfully creating new blocks. So instead of committing electricity to create new blocks, they're committing their stake of coins. Proof of work is simple, because there's no need to punish bad miners that try to validate the wrong blocks that don't fit to the rules of the node network. Their punishment is that they spent electricity on blocks that weren't valid, thus losing money. They self-inflict their own wound, so it rarely happens. Proof of stake is more complex because there is no connection to real-world resources. Without a connection to real-world resources, like energy, stakers can attack the blockchain without any punishment. Proof of stake works around this problem by taking away stakers' coins if they vote improperly. This solution comes with a few trade-offs, one being complexity. An Ethereum developer recently described the complexity issues facing their proof-of-stake system. In Ethereum's history, complexity never decreased. Every EIP is piling on top. Every major change is one more nail. I'm extremely frustrated when a research proposal says everything's figured out. It's just engineering now. I must emphasize that Ethereum is not going in a clean direction. Tangentially, it's achieving results, but it's also piling complexity like there's no tomorrow. If the protocol doesn't get slimmer, it's not going to make it. We are already past the point of anyone having a full picture of the system. This is bad. I can't say what the solution is, but my 2 cents is to stop adding features and start calling, even at the expense of breaking things. There are less and less people knowing and willing to piece together a broken network, and each change pushes more away. The last sentence should be taken seriously. A lead developer of Ethereum basically said if the protocol continues to get more complex, less and less developers will be able to grasp its complexity, putting the system at risk. Samson Mao, a developer in the Bitcoin ecosystem, describes this complexity issue from another perspective.
There's a lot of problems with proof of stake, why it cannot work. And if you fix one of the problems, you create another problem. So the general trend is for proof of stake proponents to create a very, very complex system so that the flaws cannot be easily identified.
So proof of stake is a more complex system that will take away stakers' coins if they vote improperly, and has ways of checking to see if they are voting on multiple chains. Another developer for Ethereum, Ben Edgington, explains the long-term challenges that Ethereum has faced as it undergoes its multi-year shift from proof of work towards proof of stake.
The reason it's taken a while, we've relied on proof of work in Ethereum for 5+ years, is that proof of stake is complicated. Proof of work is fundamentally very simple. It's easy to analyze, it's easy to implement and deploy. And proof of stake has a lot of moving parts. You can code up a proof of work algorithm in 100 lines or so. Our current clients are, 100,000 lines of proof of stake. And I think the theoretical foundations for proof of stake have taken time to mature. It's not obvious how to make it robust. There are attacks like long-range attacks and things which just don't exist in proof of work that we've had to think through and come up with solutions to. So that's just taken time. So meanwhile, we've relied on the tried and tested proof of work algorithm, and it served Ethereum well.
Besides this larger complexity, trust, and attack surfaces, another risk with proof of stake is centralization. With a proof of stake system, the more coins you have, the more voting power you have. And those with the coins are also the ones earning the new coins from staking. Since they don't need to expend resources to stake, they can increase their overall staking amount by earning ongoing coins from staking rewards.
So basically that would be like a political system where the more money you have, the more power you have. And in addition, for every $100 you have to vote, you would get paid $1 from the government for voting. So let's say there's a high school teacher with $20,000 in net worth. If she voted with all that money, she would get $200 from the government for voting. Whereas if you had somebody like Jeff Bezos with $200 billion in net worth, if he voted with all that money, he would get $2 billion from the government for voting. So by a factor of 1 million, Jeff Bezos would be a more valuable citizen than the high school teacher, and he would get paid a factor of 1 million more by the system for already being wealthy.
Eventually, power would likely consolidate, with a handful of multi-billionaires controlling most votes and ruling everything. If it gets too centralized, that kind of defeats the purpose of a decentralized blockchain. Instead, that proof of stake system mainly works well for stakes in centralized private property, like corporations. In a corporation, each share is worth a vote for proposals and board seats, since the owners decide what the company will do in proportion to their ownership. So suppose they are more like a corporation. In that case, the proof of stake model isn't bad for cryptocurrencies to use for experimentation. In fact, proof of stake can increase the cost of attacking the protocol, since attackers would need to acquire a lot of the coins. But of course, they'll be prone to centralization, but that can be okay if there's competition. If their service isn't good, people can go elsewhere. The creator of Proof of Work, Adam Back, describes why he thinks Proof of Work outperforms Proof of Stake when trying to be a money-like asset.
It's a system that works because money has a cost. I think money that doesn't have a cost ultimately ends up being political in nature. So people closer to the money, so-called Cantillon effect, are going to be advantaged. People with the purse strings to create more money have enormous political power.
Lynn Alden also takes a similar stance to Adam Back, saying why she thinks proof of stake mimics stock-like assets more than monetary assets.
Right, so if we're talking about what makes a good money, it's something that is inherently simple and inherently small node decentralized proof of work. Basically the leanest code you can get and distributed among as many machines as you can get and as immutable as you can get. Whereas as we layer things on top of it, like proof of stake adds a lot of code complexity. It also makes it, use my prior example, more like volatile memory than non-volatile memory. It needs to be continuously live in order to function as intended. And so when you layer those things on top of it, I would say that takes away a monetary premium, and then you can argue that it adds equity value, right? So for example, when we look at Apple stock, right? So we look at Apple stock over the long term, like this kind of meme of ultrasound money for Ethereum. You have this thing where it's mostly focused on whether it's inflating or deflating and what percentage, right? So for example, Apple stock is actually one of the most deflationary assets around. It's got a 4.5% average annual deflation rate over the past 10 years. They decreased their share count from 26 million to 16 million. And that's, of course, one of the factors for why they did well on a per share basis. But at the end of the day, what it comes down to, because they're an equity, it's the attractiveness of their ecosystem for customers, right? So it's not about how many shares they have, because you have other ones like IBM that are also rapidly reducing their share count, but because their ecosystem's unhealthy, they're not really accruing that value to shares overall. And so I think when it comes down to kind of what is trying to be money, the thing that does almost nothing other than just be money is the best money. And something that tries to do multiple things, including proof of stake as one of the components, inherently gives it less monetary premium.
In a proof-of-work system, power is distributed between miners, developers, and individual nodes. Your ability to be a miner is based on your ability to put forth money and find low-cost electricity. Rather than the original miners having an advantage and increasing their advantage over time, new miners have a technical advantage over existing miners because they buy newer machines with more processing power.
If you bought a mining rig 4 years ago, and I bought one right now, I have a bigger advantage, or I can capture more coins. That's rare that the new entrant has an advantage over the old entrant, right? So like you came into it 4 years ago. It's harder for you to capture and mine the coins than it is for me. And I think that what that does, and when you look at proof of stake, it's a little bit different. If you had first access to the coins, you now have an advantage over somebody who's now just coming in that's trying to capture them and employ them into the network.
And so from this system, Bitcoin mining businesses, old and new, are all in constant competition with each other. This is opposite to proof of stake, where there is no competition. Once you have ownership of the tokens, you can keep that power in the system forever. Plus, Bitcoin developers went to great lengths to make it easy and cheap to run a full node, which allows any user to audit the entire blockchain and reject blocks that don't conform with the rules of the network. As a result, the real power rests with the nodes rather than the miners. If miners try to collude and mine invalid blocks, the node network simply rejects those blocks.
So this system is similar to the US Constitution, where it has three branches of government. You would have the executive branch, the legislative branch, and the judicial branch. These branches would have the ability to overrule each other in certain contexts. And in addition to this overruling, they would have staggered term limits. So this is by design. You wouldn't want political people to have power forever. You would want to vote them out of office in favor of newer people with new ideas. And this is how the US works.
So like the United States, the Bitcoin network has three branches that limit each other's power. The node network has the final say over consensus, but relies on miners to order transactions and developers to create new updates that both the miners and the node network accept. Many other blockchains make multiple trade-offs, including making the nodes require immense processing power, bandwidth, and storage, so that only large entities can run them, which centralizes the network into a handful of major providers.
The point I want to make here is that this is also a slippery slope, right?
Yeah, of course.
Like, increasing the requirements by 10%, maybe Ethereum increases by 10% a year, can have an outsized effect where suddenly 90% of the people who would have done this can no longer do it, right? So it's not linear.
Yeah.
And once you start going down that path, right,
You
the reason
become
I
more
say slippery slope is you're like, well, you know, it's already hard, so it's not a big deal if we make it a little bit harder. And this is why the thought of like increasing the Bitcoin block size is so risky.
So increasing the complexity on the base layer of a blockchain makes it harder for an individual to run a full node. And without full nodes, the blockchain relies more on trust and much less on decentralization. Bitcoin's proof of work and small block design keep a lot of power with the individual users. The block size war in 2017 was a real-world test of Bitcoin's level of decentralization. Ever since the network's early history, there was a growing divide between people who wanted to increase the block size and people who wanted to keep it small. Increasing the block size allows the network to process more transactions. However, increasing the block size also increases the bandwidth and data storage required to run a full node, and in return, it puts it out of reach for the everyday user. At one point in 2017, over 80% of miner processing power, the biggest maker of Bitcoin mining equipment, and a large number of major custodians and exchanges, including Coinbase and Grayscale, were in favor of increasing the block size with an upgrade called SegWit 2x, and yet they failed.
Why did it fail? Because the plebes were against the idea. That's only possible in a network where you have so many people running nodes at home and threatening to do a UASF or something if the change proceeds. And that, I think, realistically, that would be a very difficult thing for Ethereum to achieve right now because not many people run the full nodes.
If Bitcoin were built on a proof-of-stake model, where the more coins you have, the more votes you have on how the network functions, the large exchanges and custodians could have used the millions of coins they held on clients' behalf to vote in their own favor. This is similar to how BlackRock maintains the voting rights to trillions of dollars of client assets. Proof of work and a network full of small nodes are the main way to keep a blockchain sufficiently decentralized and secure on the base layer. If Bitcoin ever upgrades to a different system, it would be only with the overwhelming consensus among users. Ethereum has also been running into more scaling problems than Bitcoin, which has opened the door to several centralized and in some ways more efficient competing smart contract blockchains. And among those new proof-of-stake competitors, there are multiple examples of their systems running into problems. One issue involved the Solana blockchain going down for 17 hours. Solana is a popular smart contract blockchain that tries to be more scalable than Ethereum by implementing a combination of proof-of-stake with proof-of-history to achieve more transactions. This higher transaction output comes with a few trade-offs. First, to run a Solana validator, you need a computer with 12 CPU cores, 128 gigabytes of RAM, and 300 megabit a second upload speed. That setup, especially the upload speed part, basically means you need to be a data center operator to run a Solana validator. Secondly, even those data center level validators have to rely on archivers if they want to go back through the full history of the blockchain, because over time, the amount of stored information becomes massive. Thirdly, Solana uses manual slashing. In other words, it's a blockchain that requires human decisions to determine consensus if there are significant attacks on the network. So Solana is not really even an automated blockchain. It's a step back from both proof-of-work Bitcoin and proof-of-work Ethereum in terms of automation, in exchange for more throughput and low fees. The consensus mechanism is more manual, human, and political. Smart contract platforms tend to move towards greater and greater centralization because the more centralized they are, the more efficient they are, and users want efficiency.
I've not gone to the step of saying that people should have Ethereum, and it's because of that centralization problem, that essentially it's this environment where you're changing the engine of a car while you're driving it. So they're going to change from proof of work to proof of stake. It's been delayed for years, and because it's a hard problem. It's a very hard problem. They keep changing how they're going to scale it. There's been inventions over the past 4 or 5 years that have changed some of their base case for how they're going to scale their protocol. And so overall, my issue with some of those smart contract platforms is that they seem like they're going to tend towards centralization. And you see that with the Solana versus Ethereum comparison, where a more centralized blockchain comes along that's more efficient because it's more centralized. And then people start kind of flocking to it. The excitement goes there. The DeFi grows a little bit quicker there than on Ethereum because there's lower fees. And they don't fully understand the trade-offs. But as long as it's working, they don't really mind too much.
As a result, smart contract platforms that have higher throughput and a massive support each have a decent shot of taking market share. The field keeps diluting itself with more efficient and more centralized networks. However, Ethereum also partially goes down from time to time with unintended chain splits, and it's possible that if it changes over to proof of stake, it could face more severe issues than what Solana faces. So overall, the main theme is that by not including upfront costs as a part of their designs, proof of stake systems inherently rely on more trust and have less ability to recover from chain splits without human intervention. Many people propose proof of stake as superior or better technology than proof of work, and they praise its higher transaction volume systems without realizing these issues. Many of the things they think are bugs to be eliminated from the system, like the fact that a proof of work system has a real-world resource cost, are features that make it as secure as possible. To summarize in a sentence, proof of work is inherently money-like, while proof of stake is inherently equity-like. What makes proof of stake blockchains inherently equity-like is that they require some form of ongoing governance, whereas proof of work blockchains are more money-like.